Hello, my name is Gunnar from Heijne, and I will give 2 lectures in this course. One on sequence profiles and hidden marker models, and one on membrane protein bioinformatics. And as you will see, some of the methods that I will discuss in the first lecture will be applied within the field of membrane protein bioinformatics in the second lecture. So with that, let's start, and I'll share my screen. So, sequence profiles and hidden marker models. So, this lecture is really about a few different methods, a few different ways to try to represent at least some of the information inherent to a multiple sequence alignment in a more computationally tractable way. That is to say, in a way that allows fast computation, fast searches, like scanning a huge sequence database with a representation of a multiple sequence alignment in order to pick up new members of a group of, or a family of protein domains, for instance, or scoring a sequence against a collection of representations of multiple sequence alignments of different types of protein domains in order to see which domains may be present in a particular protein sequence. So I will go through a few different ways to represent a multiple sequence alignment. And as a simple start, I will say a few words about maybe the first way to represent multiple sequence alignments, very simple way called regular expressions. So regular expressions is a way to represent a conserved motif, usually a short, highly conserved sequence motif in a very compact form, and a form that allows very fast searches in big databases, for instance. So as an example, I'll show this motif. It's the recognition sequence in a protein for an enzyme that adds glycans, that is sugar moieties, to a specific asparagine residue in the protein sequence. So this is called asparagine-linked glycosylation, and it's found mainly in secreted proteins or cell surface membrane proteins in eukaryotic cells. Now, this asparagine modification is the recognition sequence is a very simple one, and it's embodied in this regular expression, which basically says that to find such a recognition motif, you look for sequence motifs that starts with an asparagine, N, followed by any amino acid except proline. So these curly brackets mean that you don't allow whatever residue is inside the curly brackets. You don't allow proline, but you allow anything else in this position. Followed by a serine or a threonine, followed again by any residue except proline. So any motif that has asparagine, no proline, serine or threonine, and no proline is a prime candidate for N-linked glycosylation. And in fact, this with some qualifications, this is a very efficient way to recognize the presence of potential glycosylation sites in secreted proteins. And these are actually, although this is an old method, it's still somewhat useful, and you can find databases with big collections of regular expressions for simple motifs like this one. But obviously, this is a very insensitive way to look for sequence motifs, or find sequence similarities in databases. So it has very limited use, actually. A much more useful way of representing the information, or part of the information, in a multiple sequence alignment is to use what's called position-specific scoring matrices, or PSSMs. This is also a very simple idea in principle, and also in practice. So I'll explain it by using an example from the book. This is not protein sequence, but DNA sequence, but it doesn't really matter. So the idea here is that somehow you have identified 5 instances of some particular sequence motif in DNA. Maybe it's a motif for, it's a recognition site for a DNA binding protein, for instance, like a transcription factor. You could imagine that you've done some experiment and you have found, you've been able to experimentally define 5 or more binding sites for this transcription factor, and you have sequenced them and you found that they are 6-mers, and they have these are the instances that you found. And now what you're interested in somehow trying to condense the information in this multiple sequence alignment into a form where you can easily search, say, a whole genome for new instances of this type of binding site. So one way you can do that, a very simple way, is to use this position-specific scoring matrix, PSSM. And the way you calculate that matrix is very simple. You first just count the frequencies of each of the bases in the different columns. So in column 1, you find 60% A, 20% T, no G, 0% G, and 20% C. So those are the frequencies of the bases in that position in that first column. And then you do the same for the other columns. So you get these frequencies of appearance in the different columns. You also count the overall frequencies of the 4 bases in the whole sample. And if you do that, you find that 30% are A's, 20% are T's, 27% are G's, and 23% are C's. So these are unequal, meaning that it's more likely a priori to find an A in any position than to find a C, for instance. So the next step is to normalize for the overall frequency. So you basically just divide the frequency, the calculated frequency, by the overall frequency. So for instance, A 0.6 divided by 0.3 would give you 2. So you get this normalized matrix. Any value above 1 means that this position is enriched for that particular base, and anything below 1 means that the incidence is reduced compared to the expectation from the overall frequencies. Okay. So for instance, you could, so you see A is highly preferred in these 2 positions, for instance. And finally, and this is just for computational ease, one normally takes the log of these values. And for instance, here you take the log to base 2. So A had a normalized incidence of 2.0. So the log to base 2 is 1. Threonine had a normalized incidence of 1. So the log is 0. And this one had a normalized incidence below 1, so the log is negative. So this is your final position-specific scoring matrix. So if you now want to score a particular sequence, get some kind of measure for how well that sequence conforms to the multiple sequence alignment, basically what you do is you take the sequence and you just sum the scores for that sequence in the matrix. So this particular one, AAGACT, AAGACT, and the sum is 4.94. Now, if you take the maximum score, which would be AAG, T, C, and G, if you sum that, it's 6.68. So this is pretty close to the maximum score. So it means that this sequence fits the multiple sequence alignment pretty well. And if you took a random sequence or a large number of random sequences, you would essentially get, you would get 0, essentially. So that would be the kind of random score would be 0. So this is a very simple and straightforward way to extract information from the multiple sequence alignment that in some way represents that multiple sequence alignment, though only in part, and convert it into a simple matrix with which you can search now a big database, for instance, a DNA sequence database, to find new instances of this new high scoring hits in the database. And then, for instance, you could take the best scoring ones and test them experimentally, and in this way maybe you could find even more binding sites for this transcription factor. Okay, now this is fine as far as it goes, but obviously if you looked at big multiple sequence alignments of, say, protein sequences, one thing you noticed is that they very often contain insertions or deletions, gaps, basically. And that's, of course, if you take two protein sequences and align them using Needleman-Wunsch or some basic sequence alignment algorithm, you also find gaps. And you learned already that handling gaps is kind of what makes the alignment problem computationally more difficult, and takes you into dynamic programming to basically find the optimal alignment between two sequences. And here you encounter the same problem. So position-specific score matrices cannot deal with gaps as they are. So if you had a gap here, you wouldn't know what to do. How would you get a score for that gap, basically? It turns out that there is a rather simple extension to the PSSMs that allows you to take care of or introduce gaps as well. And that is what's called sequence profiles. So sequence profiles, also an old method. This is the original paper where sequence profiles were first proposed. As you can see, it's quite old. And here is a figure from that paper. So that's why it looks a little different from the previous figure. Essentially what this is a PSSM. It's this part here. Only notice that the matrix has been turned on its side. So you know how each row here is what in the previous slide was a column in the multiple sequence alignment. So the multiple sequence alignment runs down the vertical axis here. And the amino acids in this case, run along the top here. So it's just been turned by 90 degrees. So as I said, this part is a PSSM, where you've just taken the multiple sequence alignment. This is just a small part of the underlying multiple sequence alignment, just 4 proteins, but it's extended to much more. So this is just a small part that's been taken out. This is the consensus, basically which amino acid is most prevalent in the first position in the sequence alignment and the second and so on. And what you see is that in this early part, there are no gaps or very few gaps, meaning that you can easily represent this part with a simple PSSM. But notice here, so what they've done is they've added a final column to the matrix, and this includes or specifies a gap cost. So what they've done here is essentially to define a gap cost, and you remember this from the basic sequence alignment lecture, that gap costs can be modeled. The simplest model for a gap cost is to have one parameter for opening the gap, and then another parameter telling you the cost, giving you the cost for extending a gap. So L is the length of the gap. So if L is 1, you have the open cost plus 1 extension cost, and you multiply that by some factor, and that's the gap cost, PG prime. That's given in this column here. If you have a gap of 2 positions, then 2 residues, then you have the open plus 2 times the extend cost multiplied by PG prime. So by setting PG prime, you can basically make it very difficult to insert a gap in certain positions and make it easier in other positions, reflecting the multiple sequence alignment. So this is what this does here. So here's in the MSA, multiple sequence alignment, you see that the gap cost is high up to this point, and that's where you see very few gaps, if any, in the MSA. So all of this is well represented by just the PSSM. But now in this region, you do have gaps. And so the way that is modeled is by reducing PG prime, reducing the gap cost, making it less costly to insert gaps if you align a sequence to the profile, for instance. So so what this allows you to do now is, if you have a new sequence and you want to match it to the profile and get some kind of a score for optimal score for or an optimal alignment to the profile, you can essentially do what you do when you align two sequences, only now you align one sequence against a profile rather than a single sequence. But you can use the same kind of dynamic programming to basically allow for gaps that would improve the overall alignment between your sequence and the profile. And you can get an optimal alignment in the same way as you do with sequence versus sequence alignments. But now you have a much more sensitive, this part of the profile, or this, the profile itself, this PSSM part, of course, allows you much more sensitive, makes your alignments much more sensitive, because it focuses the alignments on the well-conserved residues, rather than treating every residue in the alignment on an equal footing as you do if you just align one sequence to another. So in this way, sequence profiles were extended in such a way that you can now use standard dynamic programming to align a single sequence against your profile. Or you can take your profile that you have defined for, say, some particular protein domain family, and you can search a big database of protein sequences, and you can score each sequence and find the high scoring candidates that belong, new candidates that would belong to that protein family. So you use dynamic programming to find the optimal alignment of a query to the profile. And here is just an example from that first paper, the original paper. So they used immunoglobulin domains. They made a multiple sequence alignment. They constructed the profile, and they ran the profile against the database of protein sequences available at that date, which wasn't very big. But nevertheless, for each sequence in the database, they calculated the optimal score, and they plotted the score distribution like this. So all of these white bars are for proteins that are unrelated to IG domains. So this is kind of a random background score distribution. And then you see that there is a small number of sequences up here with very high scores, and those are the true IG domains. And so you would define some kind of cutoff score around here, probably, that would more or less cleanly separate IG domains from all other proteins. And probably they found a couple more hits here that they hadn't included in the original profile when they did this exercise. So sequence profiles allow sensitive database searches to be made. And the fact that this was possible, or that it became so much more sensitive than just a single sequence versus sequence comparison, prompted the development of a method called SciBlast, that basically allows you to construct sequence profiles for a given protein domain family in an iterative fashion. So the idea is you take a single sequence, a query sequence, say an IG domain sequence, just a single one, you now blast it against your database. And of course, BLAST, as you remember from previous lectures, is a very fast way to, even if it's somewhat approximate, but it's a very fast way to find high scoring hits in a database. So you blast your sequence against the database, you get sequence homologs, you use some cutoff for e-value cutoff for which to include. And then you take all the homologs you found plus the query and make a multiple sequence alignment, convert it into a profile with proper gap weights. use the profile in a new blast search against the database. And because the profile is much more sensitive than the single sequence, you will most likely pick up additional homologs in the second search. Now you include those homologs, make a new multiple sequence alignment, make a new profile, and iterate the process. So search again, make a new profile, search again, make a new profile. And in this way, you can very quickly build up a very nice, very sensitive, very all-encompassing sequence profiles for a given, for starting with just a single query sequence. There is, you have to be a little bit careful when you do this, because if you include too many sequences here, some that are not actually homologs, you will start to pollute your sequence profile, and it will start to include proteins that are actually not part of the domain family you're interested in. But so what you can do, or what the method actually does, SciBlast does, is when you have at a given iteration, you take your profile, you run it against the whole database, you collect all the scores from all the sequences. And of course, the great majority of the sequences will be unrelated to your protein family, protein domain family. And so they will give random scores. And here is an example where you get a score distribution when running against a big database. The true hits will be over here somewhere, and they're very few, so they hardly show up. The great bulk are just, from the point of view of the sequence comparison, random hits. And so the score distribution of this turns out, can be very well approximated by what's called an extreme value distribution. And that's the dotted line here. Now, once you have fit your observed count score distribution to the extreme value distribution, you can use the latter to calculate e-values. So you can say anything with a score above 70, for instance, has an e-value less than 10 to the minus 4 or 10 to the minus 3. That is to say, the probability to find a sequence when you search a random database is less than 1 in 1,000, for instance. So here you can set an e-value, and you say that I will only include new hits if they have e-values less than 10 to the minus 3. And in that way, you can carefully avoid including spurious hits in your next iteration, and thereby polluting the profile. So I think it says in the book, beware of profile drift, which is just this thing. You have to be a little bit careful not to start including homologs, sequences that are actually not homologs, and polluting your profile. Okay, so sequence profiles are quite a nice advance in the protein alignment field, and that takes us to the last method I will discuss in this first lecture, and that is hidden Markov models. Hidden Markov models can be even more sensitive than sequence profiles when it comes to finding distant homologs to a protein family, for instance. And these are from the machine learning field. So I will introduce them by discussing for a few minutes a toy problem that I borrowed from Wikipedia. But I think it kind of illustrates the basic ideas behind hidden Markov models quite nicely. So this is nothing to do with sequence alignments. It's just to illustrate the thinking behind or the idea behind hidden Markov models. So the story behind this toy model, is that you have two friends, Bob and Alice. They live in different towns. And Bob has this funny habit of sending a text message to Alice every evening, telling her what activity he has been engaged in that particular day. Now, he's not very imaginative, so he only has 3 different activities. He either takes a walk, in a given day, he either takes a walk, he goes shopping, or he cleans his house. These are the only 3 activities he ever engages in, and he only does 1 per day. So Alice gets this, sequence every evening. She gets walk, clean, next evening, clean again, shop, clean, walk, etc. So she gets a long series of observations from Bob. Now, in reality, Alice is not particularly interested in what Bob does with his life, but she's extremely interested for some arcane reason in what the weather is like or was like in Bob's town. And she has no direct way of finding out. This was pre-internet days, so she cannot just check a weather site to see whether the weather was rainy or sunny on any given day in Bob's town, but she's very, very keen to find out. So she comes up with this idea that maybe she could construct a hidden Markov model that would help her predict what or derive what the weather was like, say, the 7 days last week, from the information she has available, namely the activities of Bob. So she's after this information, what's called the hidden states, because she has no direct access to this information, whether it was rainy or sunny. But she does have access to the observations. And so from the observations, she will try to infer what the weather was like on any particular day in the past week. So these are called hidden states in general in hidden Markov models. So you have a set of hidden states that generate observations, and the observations are what you have available. Now, how does she do this? Well, so she draws out this architecture of the hidden Markov model, which encompasses her idea that she should be able to predict rainy or sunny from the observations. And then she defines what's called transition probabilities between the hidden states. So, for instance, this transition probability says that if you have a rainy day, the probability that the next day will be sunny, that you will make a transition from a rainy day to a sunny day, is 0.3. Likewise, if you have a sunny day, the probability that the next day will be rainy is 0.4, that you will make a transition from sunny to rainy. If you're on a rainy day, of course, it can also remain rainy the next day, and the probability for this is 0.7, so that the total probability is 0.3. On a rainy day, you either go to a sunny day or you remain a rainy day for the next day. And likewise for sunny days. So this obviously can, if she has some historical records of rainy and sunny days in Bob's town, she can calculate these or estimate at least these probabilities. So she can say, okay, I know historically from last year that on average, a rainy day was followed by a sunny day 30% of the time, and the next day remained rainy 70% of the time. So from previous data, she can estimate these transition probabilities. So that's called her training data, this historical data. And also, if she has some training data, some historical data from earlier in time, where she can pair Bob's activity with the weather that particular day. So she knows that 3 months ago, on a rainy day, if the day was rainy, there was a 0.1% probability that Bob would take a walk and a 0.5% probability that he would clean his house. Then she can also estimate these transition or these emission probabilities, as they're called. What's the probability that he will take a walk on a rainy day? So now she has calculated all these probability values from historical data, from a training set. And now she's all set up to use new observations coming from Bob to essentially infer the most likely daily weather in the past week in Bob's town. And the way, and so she can take, given a sequence of walk, shop, and clean observations, she can actually figure out what is the most likely series of daily weathers to explain that particular series of observations. It won't be perfect, it won't be a perfect prediction, but it will give her a pretty good idea of what the weather was like. Which sequence of rainy and sunny best explain a given sequence of observations that she received from Bob. So this is the basic idea of HMMs, is that you can use a series of observations to infer the most likely series of state transitions or hidden states that generated that series. Now, what does this have to do with multiple sequence alignments? Well, it turns out that you can formulate or you can represent a multiple sequence alignment very efficiently in the form of a hidden Markov model. And I'll just show you this straight away. This is the typical design of a hidden Markov model that can represent a multiple sequence alignment and allow you to search big databases or to take a sequence and see whether it fits this particular multiple sequence alignment or not. So here is a multiple sequence alignment, or a small part of a multiple sequence alignment. And what's typical, as I said before, is that multiple sequence alignments not only have rows that contain all matched sequences, but sometimes there is insertions, a given sequence, while most sequences don't have this glycine. A few sequences have an extra amino acid in this particular position. So that's called an insertion. And other sequences might have a deletion in certain columns. So they're actually missing. They're one residue shorter. These proteins are one residue shorter. So they've lost, they're still in register before and after, but they've lost a particular residue here. And these, in protein structures, these insertions and deletions usually happens in loops or turns between secondary structure elements. So if you have two alpha helices connected by a turn, it's quite easy to insert an extra residue in that turn or to delete a residue from that turn without affecting the overall structure of the protein. So you can have, it's not unlikely to have insertions and deletions, especially in surface exposed turns between, say, secondary structure elements. Now, how would you represent such a thing as a hidden Markov model? Well, here is the typical design. So all of these are hidden states. But you see, the architecture of the HMM is a bit more involved than, for instance, the Alice and Bob architecture. So here, on this level here, you have what's called match states. So those are states where you basically, which each represents one column in the sequence alignment. So match state 1 would represent column 1, match state 2 would represent column 2, 3, column 3, 4, column 4, 5, column 5, okay? Then you have delete states. And notice that the delete state, you can bypass a certain match state, you can bypass a certain column by using a delete state. So instead of going from column 1 to column 2, you can go from column 1 to delete state and directly to column 3. So you have a transition probability for that. And of course, if you go from a match state to a delete state to another match state, it basically means you don't have anything there. You basically connect this residue to this residue, just as you do with the delete state, right? So you're missing this residue in that particular sequence. And finally, you have insert states that allow you to insert extra residues between two columns in the alignment, like this glycine here, such that let's say you're here in column 3, match state M3. Now, instead of going to M4, to column 4, you go to insert state 3, which represents this glycine here. And then you go back and you insert the glycine, and then you go back to M4 and you continue. So with this somewhat more complicated architecture, you can represent ungapped alignments when you just follow M1, M2, M3, M4, M5. You go from M1 directly to M2 to M3, M4, M5. Or you can introduce deletions in your when you have a sequence and you want to align it to the multiple sequence alignment, or you can represent insertions. And you can also represent multiple insertions. So you can insert one residue between M1 and M2, between columns 1 and 2, or you can loop back and insert a second one or a third one. So you can represent insertions of different lengths here. And of course, you can also make multiple, you can delete multiple residues by going through a delete state and to another delete state, and then back to the main match states. So that's the overall architecture that allows you to represent both matches, deletions, and insertions in the form of this hidden Markov model. Now, for the specific multiple sequence alignment here, you also have to have emission states that emit residues according to the incidence of that particular residue in a given column. So in match state 1, for instance, asparagine happens to be very frequent in the first column. So that's modeled in the HMM by saying that the emission probability of asparagine from state M1 is high. So it's a big, large character here. Threonine is also there, but not quite so high frequency. So it has a decent emission probability, alanine as well, and serine as well. And then, of course, there are some residues that are very low frequencies here, and they have correspondingly low emission probabilities from M1. And so on for the other residues here, or for the other states here. Delete states obviously don't emit any residue at all. And insert states do emit residues, and they also have specific emission probabilities. So for instance, here, where we have observed a glycine, inserted glycine in one of the sequences, that is reflected in the emission probability for glycine being high from this particular insert state between M3 and M4. And also because we have observed one here, the transition probability from M3 to I3 is fairly high, meaning a thick, as illustrated by the thick arrow here, and the return and the transition probability from I3 to M4 is also pretty high, as is, of course, the transition probability directly from M3 to M4, because most sequences don't have this insertion, right? So now we have defined the from the multiple sequence alignment, we can estimate, and of course it's much more complicated to estimate the transition probabilities and the emission probabilities here, especially the transition probabilities, the optimal ones to represent a given sequence alignment than it was in the Alice and Bob case, but there is algorithms that allow you to do this in a systematic fashion to arrive at a good choice, even if not the absolute best choice, but a good approximation to the or estimate of the transition probabilities, all these different transition probabilities that describe or best represent a given multiple sequence alignment. So with that, with all these transition and emission probabilities defined, you now have an HMM that represents in a pretty good way the information inherent to the underlying multiple sequence alignment. So what you can do now is, for instance, you can score single sequences against the HMM. So you can calculate essentially the probability that a given sequence matches the HMM. You can get some kind of score, matching score. So how does that work? Well, you can take the sequence here, A, C, G, Y, E, and you can ask, does it fit the HMM well? Well, so what you do then is you start out in M1, or rather you start out in the start state, and now you have the most likely transition, the highest transition probability is to M1. And so you try M1 and you look, okay, yes, M1 has a pretty high emission probability for alanine. So that looks good. It has a high transition probability into M1, and the emission probability for alanine is high. So that looks good. Now you turn the crank one time. So now you have a choice to go to M2 or to go to D2 or to I1. Now the highest transition probability is directly to M2, given the sequence alignment, underlying sequence alignment. And in M2, you now have to emit a residue, and indeed the emission probability for cysteine is high. So that also, that looks like a good, you have high probability to go to M1, high probability to go to, and a high one to emit alanine, high to go here, and a high probability to emit cysteine. So it looks good so far. And now you continue, high transition probability to M3, and indeed glycine has a high emission probability, so that's also a good fit, contributes to the high score. Same thing again, high transition probability, reasonably high emission probability for tyrosine, and also for the last step. So if you multiply all these probabilities together, the transition probabilities and the emission probabilities, you get the overall probability that the model would emit this particular sequence. And you will find that compared to many other sequences, most other sequences, this has a very high resulting probability. So this is a good match. This sequence is a good match to the HMM, and therefore also a good match to the multiple sequence alignment. So if this were to represent, say, a protein domain family, you would conclude probably that this one is a new member of that protein domain family. Let's try one other example, SCGGLQ, and ask how well that fits. Well, we do the same thing. We start out here. We take the most probable route first. We look, okay, serine has a good emission probability, looks fine. Cysteine looks fine in M2. Glycine looks fine in M3. But now if we transit to M4, which is a pretty high transition probability, the emission probability for glycine in M4 is low. So that would reduce the score for this particular sequence. But now we have an alternative, because the transition probability from M3 to I3 to the insert state is also pretty high. And that is because of this observed insertion here, right? And when we come to I3, the emission probability for glycine is also high because of this underlying glycine in the underlying MSA. So this is actually a fairly good route to take. It's a decent probability here. It's a decent probability to emit glycine, and it's again a decent probability to go back to M4. And then we go to L and Q, which are good, have good emission probabilities from M4 and M5. So this means that this is also a pretty high scoring sequence, even though it has an extra insertion here. It's one longer, right? So this is also a pretty good match. And you can do this, you can go on and do this for any sequence you want, and you can score any sequence you want. So you can take the HMM, you can run it against a big database, you can get all the high scoring sequences out, and you can again use random scores from the bulk of the sequences to give you some kind of statistical estimates. So this turns out that HMMs are even more sensitive than sequence profiles, and mainly because they treat insertions and deletions separately and in a more sensitive way than the sequence profiles do. So HMMs have become very useful and very much used. For instance, there is a heavily used database called PFAM that contains a large collection of protein domain families represented first of all by multiple sequence alignments and then the corresponding HMMs. So for instance, if you have a new sequence of a new protein, you can submit that to PFAM, and it will check it against all the thousands of HMMs that it has, predefined HMMs, and it will output basically the matches. So here is your query sequence, and here are the matches that PFAM made to different types of domains: a CH domain at the end terminus, a row GEF domain here, a PH domain, and an SH2 domain. So clearly, if you have especially multi-domain proteins, this can quickly give you an idea of what kind of functions this protein might have, for instance. So sequence profile HMMs are very useful. Now, the last thing I want to say a few words about is how you find the most likely, how you can find the most likely sequence of states given a sequence of observations. This kind of takes us back, for instance, to the Alice and Bob problem. Given a sequence of activities coming from Bob, in practice, how will Alice go about to infer the most likely sequence of states, that is, the most likely sequence of weathers that to give rise to that set of observables, of observed states. So another simple toy example, a very simple HMM with only 3 hidden states, X, Y, and Z. And in each state can emit 3 different characters, A, B, and C. And with these emission probabilities, you see they're different in the 3 states. And you basically have, in each state, you have a possibility to stay in that state with a certain transition probability, or to transit to the next state with another transition probability. So this defines the HMM. And now in this toy example, we say that we have an observed sequence BAB. So that has been emitted from these hidden states. We also impose the rule that we have to start in X and we have to end in Z. So we have to somehow go from X through Y to Z. And in doing that, we have to emit 3 characters, BAB. And the problem is, how do we find the most likely sequence of states? We start in X, but of course, we can then remain in X for one step, or we can go directly to Y and perhaps remain in Y for one step, or we can go directly to Z and perhaps remain in Z for one step. So there are a couple of different ways that we can move through this HMM and generate. So there are a couple of different ways that we can generate the BAB sequence, right? And we want to infer the most likely one, which state sequence is most likely to generate the observed sequence BAB. And we can work this out using this little diagram here. So here we have the 3 states, X, Y, and Z. Here we have the first step, second step, third step. Well, first step, second step, third step. You can see this as a time series if you want. And in the boxes here, you have the probability at step 1, at the first step, to be in either of the 3 states, and the probability after 1 step to be in the 3 states, after 2 steps, and after 3 steps. So the rule was we have to start in X. So at time 0, probability to be in X is 1. And the rule was that we have to end up in Z. So at the last step, the third, after we've taken 3 steps, the probability to be in either X or Y should be 0. And there should be some probability to be in Z, and while having generated BA and B, right? So here's how it works out. So we start in X at time 0. Now we have a choice. We can either stay in X, and the probability to do that is 0.8, and we should generate a B, so the probability for that is 0.2. So the probability to stay in X and generate a B is 0.8 times 0.2, 0.16. So after 1 step, our probability to have generated a B and still be in X is 0.16. But we do have another option as well. We can go straight to Y, and the transition probability is 0.2, and then generate a B, and the emission probability is 0.1. So the probability for this to emit a B to go to y and emit a b is 0.2 times 0.01, 0.1, so 0.02. So after the first step, where the probability to have emitted a b and b in x is 0.16, b and y in 0.02, and of course we haven't been able to reach z yet, so the probability to be in z is still 0. Now we do take another step. If we happen to be in this state in x, well, obviously we have now to go to y, otherwise we wouldn't reach z with 3 steps. So we cannot stay in x anymore. We have to go to y, and that's done with a transition probability of 0.2. Any other, if we choose to remain here, we will not generate the BAB sequence and end up in state 3, right? So we have to move from A to B, transition point probability 0.2. We then have to generate an A, emission probability 0.1. So times 0.2 times 0.1. And we had initially a probability of 0.16 to start out here. So we multiply these 3 together, 0.16, 0.2, 0.1. And that's the contribution to the probability of the state Y after 2 steps, if we take this route. But we can also come by this route, right? We had a probability of 0.02 to be here, that is to be in Y. And now we have a choice as well. We can stay in Y, probability 0.2. We can emit an A, probability 0.1. So 0.02 times 0.2 times 0.1 gives us a certain probability here. And if we take the sum of this one and that one, we get 9 over 2500, it turns out. So after 2 steps, this is the probability that we have emitted a B and an A and find ourselves in state Y. But we could also start out in Y and go directly to Z with a transition probability of 0.8 and then emit an A, and that's an emission probability of 0.5. So we can go from Y to Z and emit an A with this probability, multiply it by 0.02, and it turns out this is 1 over 125. So after 2 steps, we have generated a B and an A and 0 probability to remain in X, this much to remain in Y, and this much to be in Z, right? And now the final step, and we have to generate a B in the final step. If we're still in Y, well, then we have to go on to Z because we're supposed to end up in C by that rule. We do that with probability 0.8, and we emit a B from Z with a probability of 0.2. So 0.8 times 0.2 times 9 over 2500 is this much. Sorry, is part of this. It's a certain number here. On the other hand, we can also be, if we start out here when we're in Z and have generated B and A, we can then remain in Z. We can just make a transition back to itself. And of course, since there's no other state, this is a probability of 1. So we stay in Z with a probability of 1 and then generate a B probability 0.2. So from here to here, to generate a B, this is probability 0.2. So now we can multiply this by 1 by 0.2 and add it to the product of these 3. And then we get the total probability 34 over 15,625. This is the total probability that we can generate, BAB sequence starting in X and ending in Z. So this is the total probability out of all other possible 3-mers that we can generate from this model, right? So this describes all the possible transitions in the model, so all the different states. And now the last question we ask is, which is the most likely sequence of states here to generate BAB and end up start in X and end in Z? So now we basically backtrack, and this is similar to what you do in dynamic programming, actually. So we backtrack from the last final state, and we ask the question, what's the probability that we came to the last state from this one here? Well, the probability that we ended up here and came through this state is the probability that we were in this state, 9 over 2500, times 0.8 times 0.2. So that's about 6 times 10 to the minus 4. So the total probability that we ended up in this state coming from any path that passes through this state is 6 times 10 to the minus 4. And the other possibility is that we came from this state, and it turns out, so 1 over 125 to be in the state times 0.2. So that's about 1.6 times 10 to the minus 3. So it's more likely that we came through this state than through this state, right? So this must be on the path of the most likely sequence of states. So now we're here, and now we have to ask ourselves, how did we get here? Where there's really only one possibility here. So there's no choice. We don't even have to make the calculation. We have to go this way. So in order to reach here, we had to come through this state. And in order to reach this state, we had to come through this route. So this will be the most likely sequence of states to generate the sequence BAB from this particular multiple sequence alignment. And of course, we can do that we can calculate the probabilities for. So yeah, so that means that the answer to the question is the most likely sequence of states is XY, ZZ, if you want to generate the BAB sequence. So this is the so-called Viterbi algorithm applied in a very simple case here for finding the most likely sequence of states. And we will find in an application in the next lecture, we will find an instance where it's important to be able to calculate this most likely sequence of states. So in summary, this lecture has presented a few methods from very simple to more complex to represent the information inherent to a multiple sequence alignment. Regular expressions, good for very small, very short, very highly concerned motifs, but not so much for anything else. PSSMs, good step on the way, but they cannot handle gaps. Profiles can handle gaps and provide very sensitive, are very sensitive if you search big databases for instances of say, a protein domain family represented initially by an MSA. And finally, HMMs that provide even more sensitivity, even more sensitive searches, and are very good way. It's a very good way to represent multiple sequence alignment. But there are still shortcomings. So, for instance, an HMM cannot, in a simple way, represent long-range correlations. Say that in long-range correlations in a multiple sequence alignment. Say that you have in a protein family, you have two residues that happen to be close to each other in space, and one is represented in column 1 of a multiple sequence alignment, and the other one is represented in column 5. These two happen to be close in space. Now, there is a good chance that if one is mutated in, say, the first column, then you have to make a compensatory mutation in the 5th column, because these are close in space. So if one becomes bigger, the other has to become smaller, and vice versa. So this kind of correlation would be present in the multiple sequence alignment, but it would not be captured by the hidden Markov model, at least not by this sort of simple hidden Markov model. You cannot encode correlations between different columns in that way. So it doesn't represent all the information in a multiple sequence alignment, but it represents a good part of the information, and it allows you very sensitive searches. So that's the end of the first lecture, and I'll be back with a lecture on the use of some of these methods in memory and protein bioinformatics.